Okay, have you ever just stared at a completely frustrating everyday problem and thought, man, there absolutely has to be a better way to do this? I mean, we all have those passing thoughts, right? But how exactly does a simple, fleeting idea transform into a tangible, physical product that you can actually go out and buy on a store shelf? Well, today, we're going to break down the exact anatomy of invention. And to make things really concrete for us, we're actually going to build something together throughout this explainer. Let's just imagine a world without a lawnmower. Our problem is simple. The grass is way too tall, and using hand shears is giving us terrible blisters and taking hours of our weekend. So, let's invent a solution.
Welcome to our explainer on the life cycle of an idea. We're going to be exploring a brilliant 10-step design methodology mapped out by Dr. Kwasio Safo Ampadu. You can really think of this as the ultimate roadmap for inventors, engineers, and problem solvers. Whether you're trying to invent a life-saving medical device, some new software, or in our case today, the world's very first lawnmower, this framework is exactly how you get it done without completely losing your mind or your money along the way. So here is our complete journey for today. Dr. Ampadu's design process kicks off with identifying a need, wraps around through research, ideation, and design, and finally lands on full-scale production. It's a highly structured loop, and we are going to trace this exact path, step by step, to bring our imaginary lawnmower to life.
To make this 10-step process super easy to digest, we've chunked it into 6 distinct phases: defining the core problem, setting goals and specs, the art of ideation, analyzing ideas, detailed design and prototyping, and finally, implementing production.
Let's jump right into phase 1, defining the core problem. Because look, every great commercial success begins right here. Step 1 is taking an unstructured problem and structuring it. Usually a client, or maybe your boss, hands you a super brief unstructured complaint. Something like, hey, cutting the grass takes way too much time and it hurts my hands. To actually move forward, we have to clearly define the exact gap between that current state and our desired state. So our structured problem becomes, we need a way to reduce the time and physical effort required to trim a 500 square foot lawn from 2 hours down to 15 minutes. Do you see the difference there? Now we have a real, measurable target. Once that problem is structured, we hit step 2, which is background research. And Dr. Ampadu notes this is often the most important, yet somehow the most neglected step. The golden rule here? Please don't reinvent the wheel. For our grass-cutting problem, we need to gather some info. Has anyone already patented a rotary blade? Are there similar agricultural products we can maybe just scale down? What are the actual physics involved in shearing plant matter? Because if an existing product already does 90% of what you need, you might just buy that patent or modify an existing design instead of starting from absolute zero. Assuming we couldn't find the perfect existing solution, we move right into phase 2, goals and performance specs.
Step 3 is creating your goal statement. The source material has some strict rules for this. It must be concise, general, uncolored, and provide functional visualization without being restrictive. Now, what does uncolored actually mean? It basically means keeping your own biases out of it. If our goal statement is, design a gas-powered spinning blade on 4 wheels, well, we've already restricted ourselves. A proper goal statement for our project would be more like, design a device to efficiently shorten grass evenly across a residential yard. That tells us exactly what to do, but leaves the how wide open for maximum creativity. And that brings us to the crucial point of step 4, performance specifications. You absolutely must define what the system must do, not how to do it. These specs act as a sort of contractual definition between you and the client. For our mower, these indicators might be, it must operate on uneven terrain, it must cut grass to exactly 2 inches, or it must be safe enough to prevent flying debris. These indicators beautifully define and constrain the problem, but again, without restricting your freedom as a designer to find a really creative solution.
With all our rules firmly in place, we arrive at phase 3, the art of ideation.
This is honestly everyone's favorite part of the journey. Step 5 is all about ideation and invention. And you can see how it captures this beautiful dual nature. It is simultaneously the most satisfying, fun part of the process, and yet the absolute most difficult. I mean, you are literally trying to manifest something into reality that does not currently exist.
The psychological life cycle of an idea is just fascinating. It always starts with active idea generation, where you are deeply fascinated and totally saturated with the problem. But pretty soon, you hit a wall. Frustration. You just can't figure out how to make the mower cut the grass evenly. But here's the secret to problem solving: incubation. You have to relax your conscious mind. Go take a walk. And while your conscious mind is busy doing something else, your subconscious mind completely takes over, quietly chewing on the problem. And then, usually in the most unexpected place, like when you're covered in shampoo in the shower, bam, the eureka moment. An idea pops in. Wait, what if we put a high-speed fan blade horizontal to the ground?
But obviously, you can't just sit around waiting for a shower eureka moment. You have to actively trigger it. This source outlines some really specific techniques to force this idea generation. Brainstorming and mind mapping are pretty common, but there are others like the concept fan, morphological analysis, or SCAMPER. SCAMPER is a great one. It stands for substitute, combine, adapt, modify, put to another use, eliminate, and reverse. So for our mower, maybe we substitute a traditional scissor shearing action for a high-speed chopping action. By forcing yourself to use these frameworks, you make your brain look at the grass-cutting problem from radically different angles.
Okay, so now you've got a whiteboard totally full of wild, creative ideas for your lawnmower. It's time for Phase 4, analyzing and selecting ideas.
This is where those uninhibited ideas meet the harsh, cold reality of Step 6, analysis. We have to perform sophisticated technical and economic analyses on our ideas. Like, can a motor actually spin a blade fast enough to cleanly cut grass? Will it cost $10,000 to manufacture one unit? If our analysis reveals our idea fails those performance specs we set earlier, we have to drop our ego and iterate. We literally go backwards to step 1 or 2 and start again. But assuming a few of our more designs do survive that analysis, we hit step 7, selection of the best idea. So how do we actually choose the winner? Dr. Ampadu introduces this ultimate utopian checklist called the ideal final result. The absolutely perfect solution would occupy no space, have zero weight, require absolutely no labor or maintenance, and deliver a benefit without any harm. Now, obviously, no physical product is perfect, but we use comparative analysis to select the design that gets us closest to this ideal. So a massive, heavy, complex tractor mower might actually lose out to a lightweight, easy-to-maintain push mower design simply because it's closer to that ideal final result.
So we have our winning idea, a wheeled, rotary blade push mower. Now we enter Phase 5, detailed design and prototyping.
This transition from Step 8 to Step 9 is where theoretical concepts finally take physical shape. Detailed design is all about the paperwork. This is where the engineers create the CAD files, finalize the exact dimensions for the wheelbase, and dictate strict material specs, like we definitely need hardened steel for that blade. Once those blueprints are flawless, we move to prototyping and testing. This is where we actually build the thing to see if our detailed design works in the messy, real world.
And prototyping isn't just gluing some cardboard together. It's a highly calculated progression. First, we use computer simulations to test the physics, like how the airflow moves under the mower deck. Next, we might construct a scaled model. And finally, we build a full-scale physical model and run a pilot study. We take our prototype mower out to an actual lawn. And this is the moment of truth. If it clogs up with grass, or worse, throws rocks at our shins, we iterate backwards. We go back to detailed design, or even back to ideation, until that prototype works flawlessly.
But let's say the prototype works. It cuts grass perfectly, safely, and efficiently in 15 minutes. We have successfully invented the lawnmower. That brings us to our final frontier, implementing final production.
Step 10 is production. And honestly, taking a working prototype and scaling it up for commercial production brings an entirely different set of real-world variables into play. Just because you are a great inventor does not automatically mean you are ready for this phase. It requires a completely different toolkit.
Think about it. To mass-produce our lawnmowers, we now have to secure serious financing. We need to buy land to build a factory. We have to navigate human resources to hire and manage labor for the assembly lines. But the most striking requirement to me, sitting right up there next to money and land, is perseverance. Bringing a product to market is grueling. Supply chains will absolutely break, funding might fall through at the last second, and competitors will emerge. Perseverance is a literal, required resource in this model if you want to cross the finish line. And there you have it, the complete journey from a vague frustration about tall grass to a mass-produced commercial lawnmower, all mapped out through a rigorous, proven 10-step methodology. This process requires structuring your problem, removing your biases, embracing the frustration of ideation, ruthlessly analyzing your concepts, and testing your prototypes until they are perfect. So I'm going to leave you with this thought today. Now that you actually hold the roadmap, look around you. What unstructured problem in your own life, or maybe in your industry, is just waiting for you to transform it into reality? Get out there and start designing.